Okay, again, good morning, everybody. And let me first of all thank the speakers for inviting me to this workshop. It's a pleasure to be here. It's always a pleasure to be in Vienna, but it's a special pleasure because for me, at least, and I presume for many of you as well, this is the first workshop or the first conference since quite some time. At least for me, it's the first one after 2 years. And I'm a little bit rusty in talking, but you will hopefully forgive me on that. I will talk on the sparse grid tensor product approximation. For you, this is a kind of sparse grid method, which itself is a generalization of the multi-level Monte Carlo kind of technique. And we apply that to a class of generalized method of moment estimators. And they come from economics or econometrics and are special. But anyway, we try to figure out what's going on there and apply these sparse grid kind of techniques. My name is Michael Griebel. I'm from the University of Bonn. And this is joint work with Alexandros Gilch and Jens Oettershagen. So, as I said, econometric models, a strange area, but nevertheless quite interesting. These guys claim they can model economy problems and can make predictions. And it's an area with high dimensional integration problems. And this is what drew me into this field. Examples, if you are from the field, are stochastic growth models, dynamic equilibrium models, product differentiation models. Well, something which is more realistic, like a multi-country real business cycle model shows up there. And what we are after are discrete choice models. People make choices, decide on something, and one can measure that in the lab, for example. Students get in and make their decisions and on the computer, for example. And then we want to explain real-world phenomena. Or these people want to. And this involves variables or parameters that cannot directly be observed and somehow has to be estimated. They need tools to validate their theoretical models against real-world data. And this is done by the Generalized Method of Moments estimators. And the special case, which you are most probably more familiar with, is the usual maximum likelihood or log likelihood techniques. Okay? So this is what we are after. And as usual, there is an optimization principle and there is an objective function, call it Rn, which for parameterized models needs to be maximized over the parameter field. So this theta is out of RQ and denotes the examined parameter space. The form of this specific objective function S can be strange and unclear, but it depends on the model, of course, and incorporates n observed data points, call them C1 to Cn. They are out of a domain omega 1, and these points, the data points, live in R to the D1, okay? This real-world data space, omega 1, contains now all possible points of the considered economic model and are distributed, they are distributed with a probability density mu1. Okay. Now, given the parameter space and the real-world data space, the generalized method of moments and its estimator is defined as the solution of the estimating equations. And this is the usual thing. The objective function is this one, and it's differentiated with respect to the theta set to 0, and this gives us this equation here. And we see that this is an expectation over the C, over the data space of this small m for some moment function. The m is the moment function. It lives in omega 1 times theta and maps to RQ. Okay. The mu1 is unknown, and this integral can usually not be solved analytically. And therefore, in practice, and this is where many of the applications do start at the first place, this integral is approximated by a sum over the observations. So if you have n observations, you only have this guy here and not this one. Well, this is the setting. And the issue is that these observations are random samples from a real-world distribution. And we see, if we go back, that this looks like a quadrature, a Monte Carlo quadrature, if the CNs are random drawn points. The distribution is mu1, and so this is exactly an approximation to this integral by a Monte Carlo quadrature. No big deal, but this is the setting. Language is strange. Econometricians call this a simulation because they go into the lab, do the experiments, the physical lab with the students, so to speak, or go out in the field and measure something, make questions, and ask people for their choices, and therefore n is finite, and they call that a simulation. So if the small m has a finite variance, we all know what's happening with Monte Carlo. N to the minus 1/2 is the rate provided that the variance is finite, and we need that we have to have a high number of observation for a sufficiently good accuracy because the minus 1/2 is not very fast. Okay, it's all known. The other thing is that it's not so easy to approximate this setting by a deterministic quadrature, especially of higher order. This is what we would like to have, for example. N to the minus 1/2 is not fast. Let's assume that this m is smooth, then we can come up with higher order rates and get much higher speeds for the convergence, okay? So this is the setting. And now comes the first catch, namely that many of the econometric models, and this is where a lot of work went into to understand all these models, at least from my perspective, lead to functions m which have a special form. These m are capital F of an integral over omega 2 of another function psi, okay? With another distribution. Looks strange, but it comes from the fact that the omega 2 is the domain of an unobserved error variable, okay? And this unobserved second variable is integrated out. We don't see that, it's like a hidden thing. And is taken into account by this integral. If we plug everything together, we end up with a specific problem, namely the G infinity, no data points, with two integrals, an outer one and an inner one, over a function psi, okay? A double integral. The only issue is that this f is in between. If the f would be the identity in the third parameter, then this is a standard double integral over omega 1 and omega 2. No big deal. But they need this f. And for the log likelihood, this f is a logarithm. And for more complicated models, it gets more complicated. The other thing is this interior function, the psi, has a certain smoothness and lives on two parameters. The third one is the theta, on z and u. Oh, I forgot to say, the unobserved error variables are in U. The data were in Z. And the theta is the parameter, okay? Now, this is the structure where most of the models we came across fit into. A very strange thing. The F is up for debate, and the psi is, and this is the good news, it's smooth. It has mostly mixed regularity for all their applications. In the end, they are Gaussian-like, okay? So we have a structured double integral, one outer integral on omega 1 and one inner integral on omega 2 over this psi with a specific linking function. If you want, you can forget these two guys as well, but they come into play in some models. Now, this is what we are after. Of course, we need that this is well-defined, therefore need some integrability conditions. This is not the issue. And remember, we have an outer loop for the argmax optimization in parameter space. For every iteration, whatever you do with the maximization as an outer loop, we have a fixed theta. You plug that in, oh, excuse me, we plug that in and get rid of the theta for now. We are concentrating on the double integral and not on the outer loop of maximizing the theta. For each fixed theta, this is a double integral. So this appears in the inner loop of the overall algorithm. Okay. And we fix the theta and forget the dependency on theta in our notation. Now, let's rewrite the structured double integral. This is one integral with the integral f of psi, just by definition. And the second integral is here with a double integral, with an integral of the omega-2 variable of psi. It's the same thing. Just we rewrote that to see that there are two integrals showing up, an outer one which lives in Z and an inner one which lives in U and depends on Z. Okay, just a rewriting. And what we are after are quadrature rules which are high order and fast. What do we need for that? Forget deterministic and non-deterministic settings for the time being. We aim after higher rates. And to this end, we need the smoothness of these integrals. If everything is smooth, sufficiently smooth, we can employ higher order rates and gain a lot. Recall, this is in the inner loop of the maximization with respect to the theta. Any gain in the inner loop speeds up things tremendously. If we go for Hilbert spaces H1 and H2 on the two domains and have certain regularity assumptions, again, the psi has to possess mixed regularity, then we are in business and the inner integrand needs sufficient regularity in the two variables, U and C, and the outer one needs regularity only in C. Okay, if we have that, we can do something like higher order quadratures. And for these Hilbert spaces, well, we have certain choices. L2 is the simplest one, doesn't bring much convergence, but mixed Sobolev spaces are I mix.
Sorry, Albert Cohen has a question in the chat.
Oh, great.
He asks whether the measures mu1 and mu2 are explicitly known, or you just get random samples according to the...
we come to that. He has to be patient. For the quadrature, let's see that we have maybe known the measures, but in practice, especially for simulation, we do not know the mu1. And this might be later an issue. And I know what Albert is after. How can we come to higher order rates if we don't know on the measure? But for the time being, this comes later. Okay, where was I? Well, we have sufficient regularity and we need the right spaces. Let's assume we would have that mixed Sobolev HR mix in the I equal 1 and 2. These are the two domains, areas, or even an isotropic classical Sobolev space, or even analytic spaces. These are all prerequisites we could make, or assumptions we could make, and this influences our quadratures. So the approach is as usual. We approximate these two integrals by making use of the nested structure. Multi-level Monte Carlo lurks in the background, of course, or sparse grids on the tensor of the two domains. First, we consider the integration and quadrature on each problem separately, and then we plug them together either in a product rule. This is a product type fashion, full tensor product quadrature rule. Or we do it in a sparse grid type fashion, exploiting a multi-level hierarchy, which we have to construct. And this is a sparse tensor product quadrature rule, and we compare the two. Okay. Now, the full tensor product quadrature was done already for the special case of maximum likelihood for f equal a logarithm of t in an older paper. And the FTP and STP were done in another paper just recently. but just for the very simple case, which is not relevant, namely that this is the identity. This is just a double integral, and then we are back to normal. We can apply sparse grids, multi-level, Monte Carlo, higher order, whatever you want. But in this product type fashion with the two blocks, omega 1 and omega 2, this is the tensor, how we call that. And if you apply, and this is Albert's question at least partly answered, only Monte Carlo on omega 1, random variables, no known distribution, Monte Carlo should do the job. And if we have the identity, then the sparse grid rule is nothing else or boils down to multi-level Monte Carlo. If we do Monte Carlo also on the second one. Okay, but we want to apply this now for the more general moment equation case with these Hölder continuous functions. And again, if the function is the identity, you know what's happening, no big deal. If this is the logarithm, things are getting more complicated. And if this f is more complex, then you have to look into that. And I said here, Hölder continuous. This is what I assume on f, and then it works. Okay, first of all, quadratures on omega 1 and omega 2, the usual sequence of quadratures. The levels are Li, I is 1 and 2. This is a standard quadrature rule in D1 or in D2 dimensions on the two subdomains. Okay, and there are many rules. Monte Carlo, quasi-Monte Carlo, you can apply product rules, or you can apply sparse grid quadratures on omega 1 and omega 2. And their properties, as I said, depend on the smoothness of the respective integrand and therefore on the underlying space, Hilbert space we want to deal with. If, for example, we assume dyadic refinement, and for Monte Carlo and quasi-Monte Carlo, the cost is 2 to the level. If we have sparse grids, it's again 2 to the level with an additional log factor in front, which depends on the dimension. And if we have a product rule, then we have 2 to the dimension times the level, which is the curse of dimensionality. So this is the cost of all these techniques. For the error bounds, as I said, smoothness gets in, and the quadrature rule also might have a certain degree of exactness. Deterministic one at least, and the degree is pi and relates with the minimum with the regularity of the integrand. So we define an SI as the minimum of the two things, and the SI is the rate we can expect of the quadrature applied to a function from the HRI space. For mixed Sobolev spaces, we get degrees of freedom to the minus SI with a logarithmic term in front, and the Ri, which enters here, is 1 for Monte Carlo, therefore the SI is 1 as well. For sparse grid, it can be larger if there is more smoothness, and for Monte Carlo, it boils down to the usual n to the minus 1/2, but only in expectation. Okay. And I'm not concentrating on the logarithmic terms. We are after the main rates for the time being. For isotropic Sobolev spaces, we know what's happening. Degrees of freedom to the minus s divided by the dimension. This is the curse of dimension again. Okay. And then we proceed as usual with sparse grids. We form a sequence of differences. Previously, we had a sequence of quadratures. Now we form the sequence of differences in the following way. On omega 1, just this difference of quadratures of the outer function. And in omega 2, it's this difference. Here is the inner quadrature, and the difference is out of the f. So the f makes it nonlinear, of course. But these are the two differences, and this allows for sequences of difference. This allows, as usual, for a series expansion in a telescopic sum of the two integrals. And if we plug everything together, we see that the true integral, this is the one we are after, is a double sum of the two differences which are concatenated here in the right way. And the concatenation is not commutative anymore. If that f would be the identity, then we can commute the two integrations, but here it's no longer the case. We have an order in which we apply the operators. And we have a certain nonlinearity with the f showing up in the differences. But the rest is standard procedure like you might have seen in sparse grids already or in multi-level Monte Carlo. So the issue now is this is an infinite double series over two level numbers. And now we have to somehow truncate that to get a quadrature approximation. And we do this by a level index set A, which is a subset of N2. And the question is, what are our choices? Well, if we are for a full grid, then we take the maximum of L1 and L2. But here, additionally, we have a strange parameter showing on this is theta, because we are after anisotropic full grids, not isotropic squared ones. And if the theta is 1, then this is the maximum of L1 and L2. And the sparse grid index sets is just L1 plus L2 instead of the maximum. So this is the maximum norm of the levels, and this is the L1 norm of the levels. And we know that this helps a lot. We see that later in the cost. The theta, no, excuse me, the sigma is a parameter that steers the anisotropy, and it accounts for the different convergence rates and costs of the inner and outer quadratures. If they are not the same, we need anisotropic grids and so on, and balance them properly. How this is chosen, we will see in a minute. So these are the index sets. For the full grid in theta 1, this is just an index set which is isotropic in the two directions. And if we take theta 1/2, we get this anisotropic index set. Theta 2 is the other one, we call here. Theta, excuse me, I'm talking about sigma, of course. Sigma modulates this maximum. It's a weighted maximum norm or a weighted 2 norm here. And this makes these index sets getting anisotropic if the sigma is not 1. We can steer that. And for the sparse grid, as usual, this is the triangle subset, and here as well. So this is a picture of these two definitions. Okay, what do we have? Full grids, sparse grid indices, and anisotropy, which modulates that stuff. Okay, so there's a cost theorem. With the right assumptions, we get that the costs are 2 to the L. L is the level index set, which we are after. And in front of that, we have a sigma plus 1 over sigma for the full tensor product rule. And for the sparse tensor product rule, we have in the main rate a 2 to the maximum of sigma 1 over sigma if sigma is not 1. And if sigma would be 1, it's 2 to the L. And here in the logarithmic terms, we pay with +1 because it's a sparse grid, and this is what the complexity gives us. So the logarithmic terms get up a little bit. But, and this is the point, plug in here theta equals 1, sigma equals 1, then you have a factor of 2 here, whereas here you have no factor of 2, just a factor of 1. So this is twice as cheap. The sparse grid is twice as cheap as this one. You pay a little bit with logarithmic terms. Okay. If you have Monte Carlo, then you have no logarithmic terms. We made that up to incorporate all these different quadrature rules on the subdomains. Some have logarithmic terms, other ones don't. Quasi Monte Carlo have a logarithmic term, and so on. But the main rates are the important things which we are after. And then we can come up with error bounds. First of all, if f is Hölder with an exponent alpha, then we get as main rate of the error for the full tensor product quadrature 2 to minus L. And this minimum is now additionally depending on the alpha. If the capital F would be Lipschitz, the alpha is 1. And we are back to the old situation, but for non-Lipschitz Hölder functions, the Hölder exponent of this linking function between the inner and outer integral somehow has to appear, and it appears here in the anisotropy. So the anisotropy in the main rate depends on the Hölder exponent. For Monte Carlo, we can do the same thing in expectation, of course. The rates are the same. For the sparse tensor product quadrature, we get similar things, 2 to the minus L, but here is now this minimum as we had previously here, same rate. If these two terms are not the same, and it boils down to a simpler expression, if they are the same, if everything is perfectly balanced, we pay a little bit in the logarithm. But this is it. So we gain huge in the cost. Recall, this went from 2 to 1, but we pay only tinily here in the error. And this is the advantage of sparse grids, or in our case of sparse tensor product construction, provided that the regularities and the exactness degrees of the quadratures are present. Okay. What is the best anisotropy can be indeed computed, and the best one is S1 over S2, and the alpha is here in front. This is the best asymptotic error rate you can come up with. If you are in the pre-asymptotic, things look completely different, and we're not talking constants. We only were able to do asymptotics here. But this came out as the result of the optimization. As I said, it depends on the smoothness of the integrands, the polynomial exactness of the quadrature or their convergence properties, and the Hölder continuity of F. And note again, the special case, likelihood, log likelihood, this is the logarithm. Therefore, it's Lipschitz, and the alpha is 1. And this works nice. Likelihood, log likelihood estimation is a very simple and special case. So this nonlinearity and the structure between the two integrals is not so bad and can be controlled if it's Hölder. And if it's Lipschitz, then there is nothing happening, at least not in the rates, only in the constants, of course. So recall this double structured integral, outer integral omega 1, f, forget this one, inner integral over psi, omega 2. And for the maximum likelihood, it's the logarithm. It looks like it is. It falls out of the blue sky, but believe me, many of the econometric models have exactly this structure with mixed regularity in the psi. And this was surprising. It made me active in the field. Before we go into that, a simple test function, 2 dimensions, one outer, one inner. A very simple inner function, psi test. Domains are 0, 1 and 0, infinity. They are not the same, but you can adapt your quadratures to that. And the f, the linking function, is the logarithm, not the identity. With the identity, we would be back to normal. So by the way, the integral can be solved exactly, and we know what we are after. Phi test is out of the mixed regularity for any R1 and R2. So it's completely smooth, and we always get the maximal order for the employed outer and inner quadratures. We have the logarithm, alpha is 1. There's a technicality, we are not allowed to search too close at 0, but forget that for the time being. And in our experiments, we are in the right setting, set theta to 4. And this happens. We use Monte Carlo, transformed Clenchard-Curtis or Gaussian-Legendre quadrature on omega 1. And we do Monte Carlo, where we have to sample from the exponential now. Recall 0 to infinity was the domain omega 2. Only omega 1 was 0 to 1. Therefore, we have to sample a little bit differently, and Gauss-Laguerre, because that fits to 0 infinity. So we have to pick the right quadratures. Otherwise, this stuff is meaningless in the first place. And the green one is the full tensor product, and the blue one is the sparse one. Green and blue, and the asymptotic theoretical rates are these lines, namely the theoretical one is red, and the theoretical for full tensor products, and for the sparse one, it is yellow. And we see if we apply Monte Carlo for the outer and Monte Carlo for the inner quadrature, we see exactly n to the minus 1/2 goes with respect to, oh, I forgot to say, this is cost, this is accuracy, and we double our rate. We get twice as fast. This is the effect of multi-level Monte Carlo, so to speak. Yeah? Now, what happens if in the inner integrand we use a higher order method? The answer is nothing. This answers partly the question of Albert. Monte Carlo works fine for the outer thing where we do not know the distribution. Monte Carlo always does the job, but we do not get an improvement from the inner quadrature right now. At least we don't see that here. Same thing here. We do Clenchard-Curtis for the outer quadrature and Gauss-Laguerre for the inner one. And then we get this advantage and see here that the accuracy goes to 10 to the minus 2 with 10 to the 5 degrees of freedom. This is a completely different scale. Here we are at 10 to the minus 14 with the Gauss type and Clenchard-Curtis type quadrature, and we need just 10 to the plus 3 degrees of freedom to get to 10 to the minus 12 here. Completely different scale. Monte Carlo versus Monte Carlo would live here, whereas this one has nearly exponential convergence rate or a very high convergence rate for the different techniques. Same thing here. And we still have the advantage of sparse grids against full tensor. This factor of 2 shows somehow. Okay. So if we can harvest the higher order, we see that. But we need to be able to harvest that in our system. So combining Monte Carlo with a higher order quadrature does not give any improvement. And the biggest gain is if the two quadratures have the same order. Then this factor of 2, this would be sigma equal 1, and this factor of 2 in the exponent of the rates show. Now let's go to model applications from econometrics. We have a discrete choice model. For specialists, this is a multinomial logit model with random taste variation. And if everything boils down, that the f is a logarithm, as again, and the psi, the inner function, is this strange function. The psi is smooth, completely smooth. But as Albert says, we have to simulate the observations in omega 1. They are, by the way, j times q, the uniform distribution, but we still have random simulations here. So we take 3 different choices. We have, in the experiment, the people can pick between 3 different choices. This is j equal 3. And q is 4, and therefore we are living in a 12-dimensional space for omega 1 in this setting. You can crank that up with more choices easily. You can construct high-dimensional integrals. And we consider a multivariate Gaussian distribution as mixing distribution for the inner integral, and pick here d equal 2, where the measure is the corresponding CDF, which we know. Okay, and we apply all these different techniques, but recall on omega 1, we have random samples by construction, and Monte Carlo is used here first of all. And if we do Monte Carlo against Monte Carlo, this was a 12 plus 4-dimensional overall integral. For the 2 blocks we do Monte Carlo, then we still get this factor of 2 in the speed up. But if we replace, for example, for the inner integral, Monte Carlo by a Sobol quadrature, we don't gain anything. Does not work. Same here, Gauss-Hermite for the inner integral should work fine, does, but the combination does not give you any gain. They behave like the same. And the reason is the outer quadrature comes from simulation, as they say, and needs Monte Carlo, and the worst convergence rate dominates the overall quadrature. This is the point here. Only if they are nearly the same, you gain from the sparse grid method. Otherwise, the worst of the two quadratures dominates the whole thing. This is what we have seen. Now, probably are not familiar with that, and this is again partly an answer to Albert. If we still don't know the distribution, we can do something. Monte Carlo is not the end of the story. We can resort to so-called Bayesian Monte Carlo, which for the specialists is a reproducing kernel dependent weighted Monte Carlo. You have weights instead of 1 over n, you take general weights. And these weights are optimized in a certain way. Namely, they solve a linear equation system stemming from reproducing kernels. It's the same thing as Bayesian Monte Carlo. And if you do that and assume sufficient smoothness, everything works nicely. You see that here. Optimize weights instead of just Monte Carlo, where the other quadrature did not improve much, at least improves here by this nearly factor of 2, at least asymptotically. So we have to switch to Bayesian Monte Carlo for these things. Standard Monte Carlo does not give you the advantages of sparse grids or sparse tensor products. So this is what we learn here. And now we have to go into econometrics a little bit more. There's a famous discrete choice model of McFadden. It's 30 years old. Everybody is looking into that. I give you just the details without having to explain everything. The moment function looks like this. This codes discrete choice probabilities. These are the probabilities. Never mind, it's a detail. The point is that we have here a kink in the integrand. It's a Probit method, and all these Probit methods have kinks in the integrand. And people know what to do. You have, if you are familiar with integration, you know the Gens algorithm. It boils down, it's a transformation. It boils the dimension to j minus 1 and gives you on the unit cube a new integrand. We have to apply this Gens transformation for this problem to get rid of this kink. Otherwise, we have only very low convergence rates, of course. And then we end up with a nice behaving and smooth inner function. This is one trick. We have only one alternative. This makes the outer function looking like this guy here. But anyway, the message is the inner function is completely smooth. You can plug in every quadrature you want. And the f is Lipschitz. Namely, the alpha is 1. So everything is fine. Also for this famous model. We run it with 15 dimensions for the outer integral and 3 dimensions for the inner integral. So due to the Gens transform, we are back to 0, 1, by the way. This is also important. And of course, our quadrantures have to fit the type of the domain. If we are working in whole space, then we need another Gauss quadrature than working on 0, 1 or 0 to infinity. We have to adapt that. And we see the usual. Both domains are here 0, 1. I mean DI here, excuse me. We have random samples for the first integral by construction, and we use Monte Carlo here, here, and here. And the offshot is that the sparse approach outperforms the full tensor approach for these techniques. If we go for Bayesian, Monte Carlo, this is necessary. So these are the optimal weights, these 3 here, and it's clearly seen that standard product rule is much worse than the sparse rule. Okay, here, here, and here. And these are 10 to the minus 5, 10 to the minus 4. These are big improvements on Monte Carlo. Monte Carlo has n to the minus 1/2. Mixed Probit is a similar thing. What is time? Probably we're nearly at the end. It works the same, but the difference is now that the omega-1 integral does not stem from sampling anymore, but comes from modeling. It's a different model. To make a long story short, for these modeled outer integrals, we can apply directly our stuff and see the usual behavior. Higher order for sparse grids give faster rates. If the two quadrature orders are roughly the same, then we get the biggest gain, and altogether we get a much faster convergence rate. This brings me to the end of my talk. First of all, you say, this is strange stuff. It's not the usual physics simulation, but it's econometrics. But it's interesting. They have business cycle models at the Weltbank where they try to predict things and fit by estimating things. Their models to the data and the other way around, of course. It's interesting, and it bears many high-dimensional integration problems, and they have very specific structures. You have to look into the models. You have to be sure that the regularity assumptions you want to have to get higher orders are indeed present, and I've shown you the examples. You can say there are models where these assumptions are not valid. I agree. And it's not working, of course, but I wanted to give you the good news. In many models, it works. Logit and Probit are the two biggest techniques in these applications, and it does the job. Anisotropic sparse tensor product and sparse grids can exploit the double integral structure of these very general estimators and log likelihood as well, which was a special case. Of course, as I said, the quadratures in the two domains must fit the type of inner and outer domain. If you work on hypercubes or unit cubes, then you need a different quadrature than in the whole space and so on. This has to fit, but this is clear. The computation by sparse tensor product quadratures can be significantly faster compared to anisotropic full products, up to a factor of 2, which is good news. And the best is if the inner and outer quadrature rates have the same or similar rates, then you gain most. We get a factor of up to 2 with nearly the same accuracy. And this reduces, of course, the computational effort for each iteration step in the maximum cycle tremendously. As usual, you have a cycle, and you have a cycle in the cycle and another cycle in the cycle. This was the structure here, outer maximization, then the first integral, then the second integral. And of course, if you can make things faster in the interior of such a cycle, you gain tremendously. And we need Hölder continuity, alpha Hölder continuity. And if alpha is not 1, we have a slightly change in the anisotropy. Beyond that, again, and this boils a little, makes a comment again in the direction of Albert, we have different situations in econometrics. The one is simulation times modeling. Simulating was the outer integral, the omega-1, and there we did draw by Monte Carlo. And the inner one was modeling. And if the outer data were done by simulation, then we have to do Monte Carlo and have this n to the -1/2. And the message is, if you improve in the inner quadrature, it doesn't help. The overall convergence rate, well, if n is fixed, by the way, then things look completely different. There is no outer error. You only have the inner quadrature error. And there are many papers doing just that, namely improving that. But if you are after the true thing, the G infinity, as I said in the beginning, then you want to go with n to infinity, and then this is the error by sampling. You cannot improve. And this is the standard in many of their codes nowadays. brute forward Monte Carlo. But when we resort to optimize Bayesian Monte Carlo, you can improve also on the Monte Carlo and can harvest the higher rates. So this is the one good news. And the second one is there are many models I did not talk about where the outer integral is not by sampling, but also by modeling. And then, Albert, we know the distribution there as well. And therefore, we can directly allow higher order rules and harvest their better rates. So altogether, higher order methods can speed up calculations tremendously because they are used within the theta optimization cycle. And this makes econometric models computational feasible at all. Many of these models cannot be computed. I mean, let me make that point again. Simple one-dimensional times one-dimensional test function. And this was Monte Carlo. 10 to 5 degrees of freedom give you 2 digits in accuracy. This is not much. Here we get 10 to 5 degrees of freedom and get down to 10 to the minus 12. Either you go for very high accurate results with these higher order methods, or the other way around, you go for low accuracy, like here, 10 to the minus 4, and then you only have to invest 100 degrees of freedom. And this is the beauty of higher order methods, as you all know. Okay, so therefore things can be speeded up tremendously, and the econometric people, because they only work with Monte Carlo, what do? They fiddle around with their models. They try to come up with analytical models. And if this does not work, they try to tweak their terms in the model so that it's faster. But here we apply numerics and have a good chance to get really fast rates in a lot of applications. Not in all, but in a lot of them. So this means complicated econometric models, which cannot be computed practically by Monte Carlo because the long wait, month of waiting, can be done in a few seconds if you have the higher order approach, and that works. Of course, you need prerequisites, but this is the usual thing. You have to check all these models if these prerequisites are valid, and then you are in business. First of all, for the application, but also for the proof. This is what we do. We assume something. But the beauty is that these assumptions are really met by a lot of integral problems from econometrics. And this is nearly the end of my story. If you are interested in more details on all these models, you can look into this paper or maybe in some other which I've shown here. Okay, this is the end of my talk. I thank you for your attention and are up for questions.